Hello and welcome to the course of digital image processing using Python. I am Ahmad and we will discuss histogram specification, histogram matching and contrast limited adaptive histogram matching, abbreviated as CLAHE. So let's start with a recap. We started with a point pixel operation which requires a mathematical form of transformation or a lookup table. We know that we can make an idea about contrast of an image by knowing histogram of that image. Like we have this histogram of this input image. Initially we used piecewise linear transformation to stretch the contrast. Then in our last lecture we discussed histogram equalization, which designs its transformation using cumulative distribution like this one, and then we can use this transformation on input image and we can get histogram equalized image. And similarly we used this piecewise linear transformation for this input image and we got this contrast stretched image. So the conclusion was that histogram equalization is more autonomous and better solution as compared to piecewise linear transformations. We discussed little about this image earlier, and this is where histogram equalization did not work very well. Image on the right side is the original image and image on the left side is the equalized image. You can see the details inside the entrance of this building is totally darkened and not visible in equalized image over here. Similarly, the details on the right side of the entrance, like in this region, and the low portion of the outer wall, these are darkened and hidden in this equalized image. So there are some exceptions where we have alternate solutions to the issue of contrast. To be precise, very narrow or multi-model histogram are two well registered or well known cases where histogram equalization does not work. Like this one, histogram of this image is multi-model, like a lobe over here and then a disconnected lobe over here. Okay, let's start our new topic, histogram specification. So, high contrast does not mean that all images must portray uniform histogram. Mostly it's like Gaussian. I mean, the histogram is more like Gaussian distribution, which is a bell-shaped curve. Even this is not hard and fast rule. What is histogram specification? We can transform histogram of an image to some arbitrary histogram of our own choice, or based on some idea or estimation. As we know that the transform does not change the contents of an image, rather it only changes color tone of an image. So we can take an image and some histogram of our choice and then we can transform so that new histogram of the image will match histogram of our choice. We call it a reference histogram. Here on this slide it is discussed pictorially and mathematically, and we can implement this process. It is really simple if you know about functions mathematically and lookup tables, as we discussed in our last few lectures. So we can compute cumulative distribution like this one of an image, which is just like a lookup table in programming language. But for specification we need some arbitrary histogram which can be used as a reference or target histogram, like this one. This is the reference histogram and this is the original histogram or cumulative distribution of the original image which we want to change or transform. So in target histogram we assign a value greater than 0 to each gray level. This way we get a monotonically increasing function as cumulative distribution. It means it is an ever increasing function. In other words, there is no chance of having a set of constant values in this cumulative distribution function. So in short, we have cumulative distribution of the original image and the cumulative distribution of the histogram of our choice. And then we can read a pixel from input image, say its intensity is A, and we can map it using this cumulative distribution as lookup table to some value, say it's B, and then this B can be inversely mapped from this lookup table to some gray level A prime. I mean, this concept is just like histogram equalization, purely histogram equalization, because this is the cumulative distribution of the original image and we are transforming a pixel value from its cumulative distribution function, and we got B. Then we have to find this B in target cumulative distribution function, a lookup table. And as I said earlier that we have to find this B in this array. This is just a 1D array, so it's like inverse function, and you cannot use the lookup table concept here. So in case of inverse function, we map a value from the vertical axis to the horizontal axis. We can implement using find function in MATLAB or like np.where in numpy package of Python. So it is possible to find a value in some array and then use its index as inverse mapping. So that's like a mapping, a forward mapping and inverse mapping, and we'll get some A prime gray level and we can replace it in the original image. How to design an arbitrary histogram as a reference histogram or target histogram. In fact, we design cumulative histogram which corresponds to target histogram. So the simple solution would be to select many points along the required curve, like this one. We have Q0 at 0 and Q1 at A1, Q2 at A2 and so on up to say Qn at An. Then we can fit a straight line to compute missing values, like a straight line between these 2 points and similarly a straight line between these 2 points and so on. In this way we can compute the missing points or remaining points between A1 and A2 and similarly A3 and A4. We have already done this using a 2-point form, and we have to fit many lines between adjacent points. So in short, there would be like a set of straight lines from 0 gray level to the highest gray level, say k-1. So this first expression is a set of straight lines and are written as vertical axis as function of horizontal axis. This is the vertical axis, horizontal axis I. So P sub L of I as function of I. Whereas the second expression is a set of equations written as horizontal axis as function of vertical axis. So just to simplify, here is the one equation using 2-point form. here y as a function of x, and we have 2 points, say x1 y1 and x2 y2, and it's a 2-point form. It's a standard 2-point form, and we have written equation y as function of x, a vertical axis as function of horizontal axis, whereas the second equation is the inverse form of the first equation. Here x is written as function of y. So that's why we transformed or converted this equation to its inverse form. So we have an original image which is just like an input image, and then we would like to transform this image so that its cumulative distribution looks like a Gaussian cumulative distribution function. And similarly, another Gaussian histogram but with wider variance. This is the Gaussian histogram with small variance, where as compared to this one it's a Gaussian with wider variance, and this is its cumulative distribution. So after histogram specification, we can see that their cumulative distributions are perfectly matched, but the contents of the image are there, but with changed color tone. So this was the original image, this is the histogram of the original image, this is the CDF, or cumulative distribution function of the original image, or cumulative form of this histogram. And we would like to match histogram of this with this one, or cumulative distribution of this one. So after specification, we can see this is the output image and its cumulative distribution is perfectly matched with this one. And similarly, this is the output image with standard deviation 50, and this is the Gaussian with standard deviation 100, and we can see its cumulative distribution is perfectly matched with this specified cumulative distribution function. Here's another example where we have designed a piecewise linear cumulative distribution. Have a look at the original image, its histogram, and this is its histogram, and that's its cumulative distribution. And now observe target histogram. This is the target histogram. Now we can say that the target is to get an image with histogram where this main lobe is translated towards little left, like in this direction, and some more white color, which is in fact mentioned over here. So we would like to specify or transform this image in a way that we get approximately a histogram similar to this one. In other words, we would like to transform it so that we get more density in this region and with some white color. And after specification, we can observe that the main lobe is translated towards left, like this direction, and we can see some bright colors near cockpit area, like over here. So that's the modified image. Its cumulative distribution perfectly matches with our specified histogram, our reference, our target histogram. Histogram matching. It is a perfectly same concept with slight changes. In histogram specification, we need an image and a user-defined histogram, whereas in histogram matching, we need two different images, say IA and IB. and we want to make their intensity profile look like as similar as possible, and it is possible by matching their cumulative histogram, the cumulative distributions. So just like we did in histogram specification, this technique works well for images with similar contents, but most of the time it would be cumbersome to match images with different contents. The best application would be to merge a frame two images in one scene, which are taken with two different cameras with different light conditions. We have cumulative distribution of the original image, and this time this reference cumulative distribution is not a cumulative distribution of our choice or some arbitrary cumulative distribution. It's in fact computed using some reference image. So these are the two cumulative distribution of two images, and we would like to match their cumulative distributions, are in fact histograms. So there is a huge chance that many gray levels have zero count, hence we will have a flat or constant graph of cumulative, say a range of values in the histogram are zeros. We will get a flat response like this one, a flat cumulative distribution, because there is a zero addition for all these gray levels. So mathematically it is not invertible function, this one. If a function is flat, it's not monotonically increasing, then this function is not invertible, because if CD is flat due to zero count of the gray levels in image, when we map from here to here, here vertical axis to horizontal axis, we will get multiple values like this whole range. Like this whole range. So in case of programming, we discussed two functions, like in MATLAB it's a find function, and Python it's like np.where function. So these functions will return definitely a range of values, not a single value, because we are mapping from vertical axis to horizontal axis. If they are one-to-one function, monotonically increasing function, definitely we will get only a single value. But if a cumulative distribution is flat in some region, then it will return multiple values, because for this b value there are many values of I-axis. So in programming language there is some brute force methods. So we can select the minimum value or the median value or the max value. Remember, if multiple values are returned, then it is 100% sure that these values will be contiguous values, a range of values, because CD cannot have local minimas or maximas. It's overall it's an increasing function. There is a chance of flat surface, but there is no chance of local minima or local maxima, like a curve like this one. So that's not possible. A dip and then upward, that is not possible in cumulative distribution. This is almost same course with few lines, with few extra lines like these one. So we can write or implement these 4 lines of code in one line, but the process of this mapping and this inverse mapping is emulated in these 4 lines just for intuition. But we can write these 4 lines in 1 line. So that's the same code. In transformation, we are just reading shape of the image, then an empty array, then nested for loop just to read all the pixel values of an image. And then on line 14, we are just selecting ijth pixel value as A, just like this one. And then on line 15, it's a lookup table, a transformation, and tx is in fact has all these values of this cumulative distribution function of the original image. And this lookup table is mapping or transforming this value A to value B. So we got B over here. And then we searched B in our inverse transformation, which is in fact cumulative distribution of the reference image. And here is the way: np.where tx inv, which is the array holding values of the reference cumulative distribution, and then equal b. This will return some binary array, and np.where will return the index, which is a prime, and a prime over here. And then there is a chance that we may get some multiple values in case the histogram is flat. Then we used np.min, which in fact calculates the minimum value of all this range, and then we are saving that value to ijth location of the new image. So that's how we can match histogram of one image with the histogram of another image. By the way, this may not be the best solution, as it is quite possible that B does not exist simply in this array or this lookup table. So the solution would be to subtract B from this array and then find 0 or close to 0 values. So that would be a more improved version of this code. Then there is the imHist eq function, which is same as we discussed earlier. We called both the same function for the original image and the reference image just to compute their CDF and inverse CDF, and then we transformed original image using these 2 transformations to get the histogram matched image, and then they are displayed. All the images are displayed. Here is an interesting example. Applying histogram matching on colored images. The only difference is that you have to implement it 3 times. I mean on each channel, like red, green and blue separately. And skimage is a wonderful package that you can install using paper conda command. And there is 1 line of code to do that. Match underscore histogram. That's the original image, or our input image. Then there is a reference image. Reference is the data.coffee, this one. And then there is a flag multi-channel, and we have set it to true because our images are colored images. And then there is some plotting, we are displaying images using IamShow. So you can use the same function for gray level images just by setting multi-channel equal to false. So you can see the source image and the reference image and the matched image. So all the channels red, green and blue of this image are matched with red, green, blue channels of this image, and we got exactly a good blend of kitty and the coffee. Here is the histogram and cumulative distribution of three channels like red channel, green channel and blue channel of the source image, which is in fact kitty, and then cumulative distribution and histogram of reference image, red channel, green channel and a blue channel, and then these are the matched histogram. You can observe that the histogram of the matched image perfectly resembles, not perfectly, almost resembles the reference image, and similarly in case of green channel and similarly in case of blue channel. Here is the algorithm of histogram matching. We have already discussed in detail the Python code which perfectly implements this algorithm. Here is another example of histogram matching. The image in the center, this one, has a remarkable difference in intensity profile or tone of the colors from image on the left side, whereas it is quite similar in tone with the image on the right side, which is in fact the modified image. So that's the target image, that's the reference image. So you can observe that the cumulative distribution of the modified image perfectly matches cumulative distribution of the reference image, though there is a little mismatch in their histograms, but their cumulative distributions are perfectly matched. And that was all about histogram specification and matching. So back to our histogram equalization topic. Histogram equalization is about converting a low contrast image to a high contrast image. And image on the leftmost position is the original image, which is definitely a low contrast image, as we can, and it is clearly depicted in its histogram, which is narrow, very narrow in its width or distribution. And next is the contrast stretched image using histogram specification or some arbitrary cumulative distribution. Next is the histogram equalized image, which is little messed up in a way that it has shadowed most of the details in dark color. Whereas image on the rightmost position is adaptively equalized image. This has increased the contrast without washing out or darkening effects. So let's see how we can implement adaptive histogram equalization. So there are two methods. One is ordinary adaptive histogram equalization and another is contrast limited adaptive histogram equalization. Right now we are skipping the ordinary adaptive histogram equalization method, which in fact tends to over amplify the contrast in near constant region of the image, whereas contrast limited adaptive histogram equalization is a modified algorithm which limits contrast amplification. So there are some few steps just to implement this algorithm. First step is to convert the original image into tiles or sub images. Then select one tile, like in this image we have selected this top left tile on the top left, and this image is in fact converted to 4 tiles and we selected this top left portion. Then compute its histogram. Then clip the excess calculations or excess distributions. Redistribute this excess distribution over entire range of colors, and then compute cumulative distribution of this new redistributed histogram like this one. Then use this cumulative distribution as transformation, a lookup table with this tile or input image to get an equalized image. Then you can repeat this whole procedure or all these steps for all the tiles, and then stitch them together using bilinear transformation, and you will get these results. So the histogram equalization consider the global contrast of the image. In many cases, it is not a good idea. For example, the image on the top left position, like this one, is the original image, and its result after global histogram equalization is displayed just below this image. And it is true that the background contrast has improved after histogram equalization, but compare the face of the statue in both images, and we lost most of the information there due to over brightness. It is because its histogram is not confined to a particular region, as we saw in previous case. So you can plot histogram of these two images, the input image and equalized image, just to validate this information. So to solve this problem, adaptive histogram equalization or contrast limited adaptive histogram equalization is used. In this image, it is divided into small blocks like which are called tiles, and this image is generated using 8 by 8 tiles, like 64 tiles by default in OpenCV. Then each of these blocks is histogram equalized as usual, as we discussed in our last slide. So in a small area, histogram would confine to a small region unless there is noise. If noise is there, it will be amplified. To avoid this, contrast limiting is applied, like we discussed in last slide. We can clip we can set some clip limit, like we have set it equal to 2.0 in our this code, and then redistributed uniformly over other bins before applying histogram equalization. So after equalization and after stitching all the tiles, we got this result. So that is like some local histogram equalization, because we converted this image to 8 by 8 tiles, like 8 along rows and 8 along columns. And then each tile is histogram equalized and then clipped or redistributed and then stitched together, and we got this image. So you can observe a clear difference between this one and this one. It is perfectly equalized or contrast stretched in the background, which was dark in case of original image, even, and by preserving in fact it enhanced the contrast of the statue even, whereas it was washed out in case of global histogram equalization. There is a simple code using OpenCV. You can read some image and you can create an object. CV2 creates CLAHE and you can set two parameters like clip limit and then tile grid size. 8x8 is the default. You can set it to 4x4 or say 2x2. It depends on the details of the image, and then you can apply CLAHE on the input image to get output image, which can then be displayed or written on the hard disk. Here's another example. So you can see this is the original image, this is the CLAHE processed image. Same adaptive histogram equalization is applied on colored images. So you can see this colored image has very darkened region over here, whereas it is very clearly exposed in processed image using some bins and some parameters. And similarly, this image has a very dark region over here and clearly exposed in processed image or CLAHE processed image. So in images like this one, you can set more and more tiles because there are so many details in this image, and it's okay if you set some, if you convert this image to some lesser number of tiles, say 4x4 or 8x8 or 16x16. So let's end this lecture over here, and we will discuss some filtering and spatial filters in our next lecture. And thank you. Goodbye.